So this is a quick video on how to calculate the mass defect in a reaction. In this case, it's a fission reaction, and the information, the question itself comes from the Nelson textbook. This question here, we've got U-235 decaying or undergoing fission and becoming barium-142 and krypton-91 and producing 3 neutrons. Part A of this question is to figure out what is missing or what's wrong with the equation. And the way you would calculate that is you would just do some numbers, do some mass numbers. First of all, you can check and make sure that the bottom numbers, the atomic numbers, are correct. So U is definitely 92, barium is definitely 56. Let me just check that again. Yep, and krypton is definitely 36. The other thing you can do is say that 56 plus 36 adds up to 92, so that's good. So maybe the problem is in the mass numbers. We know that 3 neutrons are produced, and that's fine. So what we're going to do is we're going to say that the numbers on the right side, the mass numbers on the right side, must add up to the masses on the left side. So we have 142 plus 91. 142 plus 91 is 233. And then each of these is worth 1, so that's 3. So we have 3 more onto 233, which is 236. So we've got 236 on the right, and we only have 235 on the left. So that's another way to realize what could be wrong. We don't have the right numbers on the left side or right side. So either we have to take a number off of the right side or add a number to the left side. But if you remember, a fission reaction requires a neutron to initiate it. So, and you can see that on page 336. There's a good explanation of that. So we have to add in a neutron on the left side. N, 1, 0. That adds 1 to the left side, which makes it 236 as well. So there's your part A answer. Part B, we'll switch to here. So part B, I've got the equation written up. You're going to need some numbers. When we want to know how much energy comes out of this reaction, we know we're going to be doing the E equals mc squared calculation. And what we have to do basically is figure out how much mass is lost in this calculation. And you're given all the information. You're given these 3 values in the question itself. And this value, or this table of values, is in the textbook. I'll let you find it for yourself and make you do some reading. So here's how we're going to do this. We have to get the numbers. I'm going to keep it in atomic mass units to make it easier, because then I can either convert my neutron numbers into kilograms. No, sorry, the neutron numbers are given in both. So I've got neutron mass in atomic mass units, and I have it in kilograms. Well, I'm given the other ones. These are all in atomic mass units, so I might as well use the atomic mass unit in here as well. So I'm going to write those numbers in on here, and then I'll show you the same calculation. Actually, I'll do that on the next page, because I've moved everything out of the way on the next page. In fact, let's do a little bit of shrinking here. I can still read that. And that gives me lots of, oops, that's not big enough, small enough, big enough. Okay, so writing in the numbers, we get, let's bring this up here and give me lots of room. We get 1 neutron is 1.008665. The uranium is 235.044. So I'm just adding these numbers together. Barium is 141.916. Excuse me. Krypton is 90.923. And then I've got 3 neutrons, which is 1.008665. And this is all in atomic mass units. So what I want to do here to see what the mass defect is, across this reaction, we've lost mass. Okay, there's a small bit of mass that's disappeared, and that mass is converted into energy. So on the left side, we wind up, I've already done the math here, with 236.05266 I kept all the decimal places. The reason I kept all the decimal places is a very small amount of mass is actually lost. And you might, if you round this, you might not see the difference. All right, so that's what I get on the left side. On the right side, I get 235.864, let's make that bigger and clearer, 64995. So you can see there's a change, right? And it's smaller. That's a good thing. If you get a number that's bigger, something went wrong. Okay, check your math. And it's hard because you've got a lot of numbers to enter in here. So you've got to make sure that you're very meticulous about the numbers you add or plug in. So when I subtract those two numbers, I get 0.18767 mu, or u. Okay, so that is my mass defect. So now we have to do the conversions. I'm going to convert to kilograms, use E equals mc squared, and then give you an answer in joules, and then convert that to mega electron volts. So the first conversion is, we want to change this into kilograms, and we have one atomic mass unit is 1.66 times 10 to the negative 27 kilograms. So there's our conversion. All right. That gives you 3.11532, sorry, kilograms. I jumped ahead. 322 kilograms. Now, to do E equals mc squared, that's the next step. I'm going to sit down so I can write this in easily. E equals mc squared, we have to take that number and we have to multiply it by 3, the speed of light, 0 times 10 to the 8 meters per second. That's the speed of light squared. So that's the c in E equals mc squared. Okay, so right here, I'll just put this in black. We have E equals mc squared. That's what we're doing here. So that number comes out to, let's make it different from the green on the left side. So we multiply that, we get 2.80378898 times 10 to the negative 11 joules. So that would be your answer if your answer was required in joules. But in the textbook, they ask you to do it in mega electron volts, and the conversion for that is times, 1 mega electron volt over 1.602 times 10 to the negative 13 joules. Move that out of the way. Okay, and that translates, and I'm going to drop some significant digits here because we don't need as many, and the textbook asks you for 2. So that's going to give us 175.018 something mega electron volts. The textbook rounds that to 170, which is actually incorrect. It should be 180 if you want it in 2 sig digs. And that is it.